Hey everyone, so today we're going to spend most of our time actually implementing a neural language model in PyTorch, and we're going to be switching shortly from this iPad to a Google Colab notebook. But before we do that, there's one more important thing that we need to cover before you're ready to actually understand what's going on when we implement this. And that specifically is the loss function that's used in neural language models and more generally for neural classification problems, and that is the cross-entropy loss. So again, this is used in NLMs, neural language models, as well as other classification tasks. So remember, we are treating in the neural language modeling setting this task as a classification problem, right? Given a prefix, we're asking the model to predict which word out of the set of all word types in our vocabulary follows this prefix, right? So it's a classification problem where the label space is equal to the size of the vocabulary. So it's a large scale classification problem. And the loss function that we saw previously, the square loss, is not suitable for such a large scale classification problem. And so we're going to review a better one, the cross-entropy loss, before jumping over to the implementation. Okay, so quick review from last time. What is a loss function? Intuitively, tells us how bad a model is doing at predicting the training data. Right? So in the neural language modeling setting, if I have a model that gets as input the prefix students open there and is predicting the word lamps with a high probability, we want a loss function that will assign a high loss to this instance, right? Because the model is clearly not predicting the training labels if in the training set we saw a lot of examples of students open their books or their laptops or so on. Okay, so in NLMs specifically, how bad is the model at predicting the next word? Okay, so let us dive into this by looking again at the example that we've been following for the first few videos here. Okay, so assume we have a training example. Students opened there. This is the prefix, and it's paired with books. Okay, so we have our input here and our output, books. So the model takes this as input. Whoops. And this, remember, is desired model prediction. So remember that our model is actually producing a probability distribution over the whole vocabulary. So what we really want is a predicted distribution in which the probability associated with the word books, given this prefix, is very high. So to make that more concrete, our model produces, given and we want to maximize this probability. Okay. So we know that we want to maximize the probability of the correct continuation, given the correct continuation, meaning the thing that appears in our training data, given our model. So remember that a loss function is a measure of how bad the model's current prediction is. So we can rewrite this as we want to minimize, and remember we talked about gradient descent in the concept, or when we talked about gradient descent, we talked about minimizing a loss function, right? We use gradient descent to go in the direction of the negative gradient and find some sort of minimum of the loss function. So we can easily turn this into a loss function. We want to minimize the negative log probability. So remember again that we work in log probabilities, not raw probabilities, due to many reasons. Practically speaking, due to numerical underflow, right? We don't want to deal with these super tiny numbers. And in our example, we want to minimize the negative log probability of books. So our loss function is going to look like negative log p of books given students open there. So this is pretty straightforward. But before we continue here, it's important to understand why this is called a cross-entropy loss. So many of you are probably familiar from previous classes, machine learning classes or so on, with the concept of the cross-entropy loss, right? So why is this called the cross-entropy loss? And remember that the cross-entropy loss intuitively gives us a measure of the distance between two probability distributions. So if my model, let's say my model gets, maybe I'll draw the model to make things more clear. So we have students opened there. Remember that I have word embeddings for all of these things. I combine them into a single vector. And then I produce a probability distribution, right? So what does that actually look like? If we say all of our words are books, laptops, I don't know, maybe you can make up some other words, planes, lamps, etc. So all of the words in our vocabulary, right? And let's say this is what our model is doing. So maybe it assigns some probability to books, it assigns some probability to laptops, some probability to planes, a very high probability to lamps, and so on. So in our training data, we observe that, of course, the correct continuation of this is books. So we treat our training distribution, so maybe I will, this is a model, and let's say this color is used for the model's predicted probability distribution. So next we have our data, and in our data we observe students opened their books. So in this specific example, there is no ambiguity as to what follows students opened there, right? So we consider this as a one-hot distribution. Remember, we talked about one-hot vectors as a way of encoding words in an earlier video. So we can, have our same distribution here: books, laptops, planes, lamps, and this model is going to assign all of the probability, so p books given there, oops, and these are all 0. So let's make this clear. This is what we observe in our data. What color have I not used? I love this. So intuitively, we have a model's predicted probability distribution, and we have the ground truth probability distribution, which is this one hot vector, right, essentially, with one at the ground truth continuation. And we want to make the model's predicted distribution as close to the ground truth distribution as possible. So remember that cross entropy loss is defined as, okay, we'll go down here. Sorry, the cross entropy of two distributions, let's call them P and Q. This essentially, again, quantifies distance between the distributions. So if the cross entropy is low, then the distributions are fairly close together. If the cross entropy is high, that means that they're pretty far apart. And the equation for this is, so in our neural language model setting, remember that the different classes that we have are the word types in our vocabulary. Okay, and so these are the conditional probabilities that are written in short form here. So this is, we can treat as our ground truth distribution. 1 for books, 0 every other word type. Sorry, that should be 0 for every other word type. And this is our predicted conditional probs. So this is the definition of cross entropy loss, which we have ported over to our neural language model setting, where P is the ground truth distribution and Q is the predicted distribution. So maybe I'll make that more clear using the same colors from above. So we used P with this color and Q with the blue color. Okay. So let's take a look, go back and take a look at our loss function that we came up with from before, which was just followed naturally, right? We want to minimize the negative log probability of the word that appears in our training data set, books, given this prefix. If you look at this definition of cross entropy here, you'll see that since the P term is 0 for every word other than books, this simply just reduces to exactly what we had before. Given the prefix. So hopefully this makes sense. Since this summation is, there's only one non-zero term, and that's when this W equals books. Okay, so that's a bit of intuition on what kind of loss function we're using for neural language models. But the important intuition is that a loss function in our case is defining a measure of how close the model's predicted probability distribution is to what we've seen in our training data. Later on in the semester, we'll talk about methods where this here is not a one-hot vector, so you actually have to use the full definition of cross entropy. There are many non-zero terms, but for now, we're going to stick with the simple case. Okay, so that's all I wanted to say about the type of loss function we're using in neural language modeling. And now let's quickly switch over here to the Colab notebook that I want to share. So give me a second to do this. Okay. And yes. Okay, so that's too big. Okay, so now we're going to switch over to a kind of live coding exercise where I will walk you through the implementation of a very simple neural language model on a toy data set of basically, I guess, like 4 prefixes. Yeah, I highly recommend for this to be productive that you open up a Colab notebook of your own while I'm doing this and follow along with what I'm doing. There are a number of interesting places where you can branch off of the code that I'm writing and implement more complicated networks or training optimizers or architectures or so on. So I think you'll learn a lot if you code this up along with me when I'm doing it. Okay, so I'm going to click New Notebook here. Okay, this is going slower than I expected. All right, let's name this CS685 NLM implementation. So let's start by implementing the fixed window feed-forward neural network that we've seen in a previous video. So to begin, I'll come up with some sample sentences. So let's say my sentences are, I don't know, we should make them short. So maybe like Bob likes sheep, Alice runs fast, CS685 is fun. Hopefully that's true for some of you or all of you. All right. I love lip. Okay, so we have these 4 sentences. They're all 3 words long. So we're going to, let's say, do a fixed window neural language model where our prefix size is 2. So we're going to take the first 2 words and try and predict the 3rd word. So maybe I'll write some stuff down in the comments. So given the first 2 words of each sentence, we will try to predict the 3rd word using a fixed window NLM. So this is our goal. But before we do that, we have to start by doing something that you've done in homework 0, which is tokenize the input. So before we start any fancy modeling, we have to tokenize our input. And the second thing we have to do is convert the words to indices. Remember, because our model takes as input sequences of indices rather than sequences of text. So we need to do these 2 things before proceeding any further. Okay, so let's do both of these. I think the screen is still visible. Oh, maybe I should increase the font size. Okay, whatever. That's probably, hopefully it's readable. Okay, so let's start by defining an empty vocabulary. So this is going to map from word type to index. So every single unique word type in our vocabulary will be assigned a separate index. And then we'll have a list of inputs that we're going to store. So it's going to be just like the sentences, except each of the elements in this list is going to be a sequence of indices rather than a string. So stores an indexified version of each sentence. Okay, so a simple way to do this is compute the vocabulary while converting the sentences to indices on the fly. So we can loop through our sentences. Let's say we make a variable for, I don't know, sent indexes. So these are going to be the mappings for the current sentence. We're going to split on white space. So this is something you saw in homework 0. Tokenize with white space. Again, not the best tokenizer. A lot of you posted on Piazza about things associated with like new line characters or punctuation being included in the word types, and there are much better tokenizers, but this is a simple toy example. There are only white space tokenization is exactly what we want in this case. All right, so we're going to loop through the words. And for every word, we're first going to check if that word is in the vocabulary. If the word is not in the vocabulary. So if the word is not in the vocabulary, we want to add it to the vocabulary. And we also want to assign it to a unique index. So this line of code assigns it to the current size of the vocabulary. So it ensures that every new word we add, we're basically incrementing the index that we're at. So the whole point of this is to add new word types to the vocabulary and pair them up with indexes. And finally, we are going to append the index associated with the current word that we're at to the sent idx's variable. So vocab w. So this is going to, if we're at the word Bob, it's going to add a mapping in the vocab dictionary from Bob to 0, and then it's going to append a 0 to this list that I've created here. So once I've looped through all the words for this first sentence, I probably have 0, 1, 2, because these are the first 3 words in my vocabulary. Actually, I've realized that I haven't even shared any words in any of these sentences, so I guess there's 12 different words. Maybe we'll change that, so I'll make it Alice is fast. So now there's 2 occurrences of the word is. All right, and once I'm done looping through all of the words in this particular sentence, I'm going to append the whole sequence, the sent idx's list, to my inputs list. Okay, so that was a lot of stuff. Let's see what all of this looks like. So first, we can look at our vocabulary. Let me delete some of these lines. So as a tip, if you want a shortcut to run a Colab cell, you can type Shift-Enter. At least that's what it is on my Mac. And we see that every word type in our vocabulary, Bob likes sheep, Alice runs fast, is blah, 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 is assigned to a particular index in the vocabulary, and the word is only appears once, right? Because there are 2 tokens of is in our data set, but only 1 word type associated with is. Let's also take a look, just to be clear, as to what the inputs object looks like. So you see that it's a list of lists, and each list is contains a bunch of indices, right, rather than actual words. So we see here that, oh, I guess I have to run this cell again for it to update. Yeah, so we see the first sentence, Bob likes sheep, is mapped to 0, 1, 2. The second one, Alice is fast, 3, 4, 5. The third one, CS685 is fun, is 6, 4, 7. So note that the index associated with is occurs in 2 of these examples. Okay, so we're almost done with our pre-processing stuff, and we're almost on to more fun things. But before we can actually feed this list of lists into our PyTorch models, we need to convert them into PyTorch tensor objects. So this is also something you saw in homework 0. We use the long tensor object for indices. So the embedding module in PyTorch expects long tensor indices in the form of long tensors. So it's very easy to convert these things. We can simply just cast them into long tensors. So I'm going to import torch because I haven't done that yet. Okay. And let's just say, oh, right. So the other thing I want to do, so, okay, two things. One, convert to long tensors. And two, define inputs and outputs. So right now, these are just sequences, right? So I actually want to split them up into, given Bob likes the input, predict sheep, the next word. So let's do that first. We'll call our inputs the prefixes. So we know we can get prefixes by simply just chopping off the last element of each of these lists. So let's say cent, and this slicing in Python, if you're not familiar with this notation, you should make sure to understand it. But this right here is just indexing everything in this this first sequence here, except for the last, the -1 element. And I'm going to just loop over all of the sentences in my input. And this is a list comprehension. So again, for those of you who aren't familiar with Python or aren't super familiar with it, you should read about things like list comprehensions and array slicing and so on. They're very useful concepts in general. Okay, so similarly, I can create another list with just the labels. So this is the last word in each sequence, like this. So now, just to show you what I did, if I print the prefixes and the labels, so this first thing here is the prefixes. So note that they're just the first two elements of each list chopped with the last element chopped off. And the labels are just a sequence of the last element from each list. So this is exactly what we want in our language modeling setup. Okay, so again, to get these into long tensor format is very simple. All I do is wrap this long tensor thing around each one. And now, let's say I print prefixes. You'll see that I have this tensor object. It contains the exact same data, but I can do all these PyTorch operations to figure out what size this is and so on. So now we're ready to start building up our model. We have our data in input-output format in the data structure, this tensor thing that PyTorch expects. So let's move on to the next cell, where we're actually going to define the network. On to defining the network. So this is where most of the fun stuff happens. Before we start, let's import, just for to make it easier for me to type things, this shorthand. And so the first thing we're going to do is make a class for our neural language model. And so all neural networks, when you build them in PyTorch, have to inherit from this nn.module class. Yeah. Okay, so there's two things that you need to do if you're going to use PyTorch to make a neural network. So the first thing is write the init function. This initializes all the parameters of the network. So we'll get to this in a bit, but remember, we've spent quite some time now in the previous videos identifying the parameters of various models, and then, of course, computing the partial derivatives of our loss with respect to those parameters. The second thing we need to do is a forward function. So this defines the forward propagation computations. So this is what we went through before looking at backprop, right? How you go from the embeddings to the final prediction of the probability distribution. And we did this, remember, through a bunch of linear layers and softmax layers and so on. So that's it. You just have two things to do. You might be wondering, what about the backprop, right? We spent all this time learning about how we use backprop and gradient descent to train our models. Don't we have to spend time actually implementing those derivatives? And this is the really nice thing about PyTorch, is that you don't, and it computes all the derivatives for you in just one function call. So we'll get to that a little later, but it's incredibly useful. You can implement super complicated networks without worrying at all about manually deriving the gradient. Okay, so let's start with the init function. So there's a couple of things that in our fixed window neural language model we want to define. So if you think about the hyperparameters of this model, right, the things that we want to define as the people who are making this network, and we don't want the model to learn it itself. These are things like the dimensionality of the word embeddings, the dimensionality of the hidden state. So this is, remember, when we concatenate all the embeddings together, we then project that to a lower dimensional space, right, using a linear layer. So this is defining the size of that hidden space. We may also want to define our window size for this model, which we've already looked at in our training data as 2. But note that in a standard implementation, you won't be making like static training examples like this. You'll rather be kind of incrementally constructing the window while scanning from left to right through a larger document. This is just for an example to make the pre-processing code and the training loop not super complicated. Okay, and the final thing we might want to do is tell the model how big the vocabulary is, right? It needs to know this for both the embedding parameter initialization, like how many embeddings does it need to create, as well as the softmax layer, right? How many word types do I need to predict probabilities for? All right, so the first thing I'm going to do is initialize the superclass of this, the nn.module and anything that's higher up. So init the base module class. And then I can proceed with creating parameters that are specific to my network. So I know that there are basically three types of parameters in this model. So the first is the embeddings, and we looked at this in homework 0, right? We use this nn.embedding object, and it takes as arguments, I think it should tell me what the arguments are. Okay, maybe not. But the arguments are the number of word types in the vocabulary, which we are passing in as len vocab, and the dimensionality of the embeddings, which we're saying is a de-embedding. Okay, next up we have our hidden projection, right? So we're going from the concatenated version of these embeddings to the hidden layer. So we'll make a matrix for this, or we're actually going to use PyTorch's built-in nn.linear, which does this hidden projection. Let's just name it w/hid. So we have an nn.linear, and the arguments here are essentially specifying the shape of the projection matrix. So we know in our case that we have the embedding dimensionality times the window size, because that's how big that concatenated representation is going to be. and we're going to project that to the hidden dimensionality. So this thing here is the size of the concatenated representation. So maybe I will concatenated embeddings to hidden. That's the purpose of this linear layer. And the other thing we have is hidden to output probability distribution over vocab. Okay, so we can call that self.w sub out. It's another linear layer. It goes from d hidden to the vocabulary size. Okay, so this in our extremely simple neural language model is what we're going to, these are the parameters. Currently, we haven't applied any nonlinearities. We could do that, and maybe we can do that in our forward function. Okay. Great. So let's move on then to the forward function. And the forward arguments always take an input, which is in our case going to correspond to the prefixes. So each input will be a batch of prefixes. In our case, since we only have 4 prefixes, we're just going to consider a batch of all 4 of them. In practice, of course, you would have many, many more sentences and prefixes, and so your batches would contain different prefixes per batch. So let's go back down here. In this case, 4. So that's what is going to be in this input. So you can think of the input to this forward function as the prefixes variable that we made up here. All right, so just want to make sure this is recording properly. Okay, it looks like it is. Let's go ahead and start. So this is fairly straightforward. What we're going to do is first, let's just get some statistics about the input. Prefix length equals input dot size. So again, these are the dimension. This is the dimensionality of the prefixes tensor that's going to be input here. And now let's just go ahead and get embeddings for this input. We can do this by simply calling self.embeddings on our input. Okay, so what does this look like? And in general, a good way to proceed with building your forward function is to incrementally debug it. I know people like to use debuggers and stuff. I don't really do that and instead just use simple print statements, which also works, probably not as efficient, but whatever. So let's actually construct an instance of this NLM class. So I can do that by, again, this calls the init function, so I have to specify all of these things. Let's say my d embedding is going to be, I don't know, what should it be? 5, d hidden, say 12, window size we defined as 2, and when vocabulary equals the actual length of this vocabulary dictionary. Okay, so if I run this, it's going to execute the init function. Okay, so let's make sure that it does and there are no errors. Okay, and next we are just going to pass our prefixes through this forward function. So if I do, and you don't even have to call the forward function, you can just write this and it automatically calls the forward function that you've written. So just to make that clear, if I print the size of this embeddings object, I get 4 by 2 by 5. So it's a 3-dimensional tensor, and let's think about why it's this is the dimensionality of this m's variable. So 4 we know is the number of prefixes in this tensor, right? We have 4 examples. So this corresponds to the batch size. 2 is the number of words in our prefix, right? The number of words in the prefix is 2. So in the first example, our prefix is Bob likes. And so we have an embedding for each of those words. And 5 is the dimensionality of our embeddings. So for each of the 4 prefixes and each of the 2 words in that prefix, we have a 5-dimensional embedding. So that's how you can interpret this. Okay. So now that we have this, what's the next step? And let's just write the dimensionality out so we can have it as reference for later. So in the neural language model, next we want to concatenate the prefix embeddings together. So here our window size is just 2, so we're going to concatenate these 2 dimensions together, and these 2 embeddings, each associated with the prefix together. So our ideal expected output is going to have a dimensionality of 4 by 10, right? The first 5 dimensions of that 10-dimensional vector are going to correspond to the prefix embedding of the first word, and the second 5 are going to be the embeddings of the second word. So in this case, we can simply just accomplish this with a reshape operation. So if I say concat ems equals ems, and the view function is a good way of reshaping your data. So I've already got this batch size, right, which I know is 4, but we're just going to use these variables in case, you know, at some other point, maybe at test time, I want to use a batch size that's not 4, right? I can use a variable number for my batch size. So I know the first, I want to keep the 4 prefixes distinct from each other. And if I put in -1, that's just going to essentially squeeze the rest of the dimensions into a single vector. But in practice, of course, I know that this is going to be window size, which I did not store here. Sorry. Can we do it here? Window size times, let me just store a variable for the embedding dimensionality, self.demp. Okay, so this simply takes this embeddings variable and reshapes it to a 4 by 10. Let's make sure this actually worked. Hopefully it did. Okay, so I'll put some print statements along the way so we can make sense of what's going on. Embedding size. And yeah, as a practical tip, the size, the dimensionality of these intermediate variables that you're creating is one of the most useful things that you can look at, because a bunch of the errors that you're going to get if you're implementing this and other more complicated networks are going to be maybe you messed up and you didn't keep track of your dimensions properly, you swapped around window size and embedding dimensionality, and now your matrix multiplications don't work, and so on. So you should always keep track of the size of the variables that you're creating in the forward function. All right, so let's print these things out. Whoops, what did I call it? Oh, DMs. Okay, so we see that the embedding size was 4 by 2 by 5, and now the concatenated embedding size is 4 by 10. So we remove the sequence dimension and just concatenate all of the embeddings associated with the prefix together to form one 10-dimensional vector per input prefix. Okay, and maybe we can validate this, right? So if I print the embeddings out for the first prefix in my my batch, which corresponds to Bob likes. So if I print this out, I get these 2 embeddings. You can see there's two separate embeddings, one on each line. And if I print out concat 0, you see there's just one 10-dimensional vector where the order here is the same as the order here. It's just we've squeezed these two vectors together. Okay, so now let's get on with the next computation. Now we project this to the hidden space. And it's very easy to do this. We can just use our linear layer that we defined previously. So I can say hiddens self.whid and concat ems. And so now if I want to look at the size of this, remember that I've specified a hidden dimensionality of 12 here. So hopefully this thing is going to be a 4x12 matrix, and it is. Great. Okay, so I've gotten to this point. Now I'm at the hidden space, and finally project hiddens to vocabulary space. And again, we just follow this exact, in fact, I will just copy this. So we'll call this out, out equals w out hiddens, and we're going to print output size equals outs.size and 11. So our vocabulary, remember, is 11 because there's 11 word types. We have this word is that appears twice, and all the other words appear just once each. So we have a vocabulary size of 11. Okay, so are we done? Well, if we print outs, we will see that these are definitely not probability distributions, right? And the reason for this is because we have not applied the softmax function. So in practice, to compute our loss function, which remember is the negative log probability of the target word, we're going to do a log softmax followed by the negative log likelihood. But PyTorch actually combines both of these into a single loss function called the cross entropy loss, as we'll see later. But just as an example, maybe I want to show that I can get probabilities out of these outputs. So I can do this by, and you saw this also in homework 0, I can apply the softmax to outs, and I have to specify the dimension. So here I want to take this over the, not the batch dimension, but the actual, the logits. Oops, I didn't print it out. So if I did this, then the resulting vectors, as you can see here, this is for the first prefix. You can just take my word for it that this sums up to 1, and you can see that all of these numbers are positive. Actually, we can even show that they sum up to 1. So these are the sums of each of the vectors, which just enforcing that we can get probability distributions out of these if we want. But for now, we're just going to return the unnormalized probabilities, also known as logits. So the logits are the values of this vector before applying the softmax. Okay, so now that we're confident that at least the network isn't crashing, right, when I feed the inputs through it, I'm going to get rid of some of these print statements to make it cleaner. And we get this as output, the logits. And you'll see here that I have this grad function thing when I print out this outs tensor. And this is what's going to allow us to perform backprop. The PyTorch just keeps track of all the computations I need to do in order to compute the gradient for everything that I've defined in my forward function. So every one of these operations, this when I embed something or when I reshape it, when I apply a linear layer, all of these have been in PyTorch sort of paired up with the functions that you need to apply to compute the derivatives whenever they're applied. And so because these things are all, this functionality is already there, we don't have to manually compute the derivatives ourselves. Okay, so let's just assume that this network is working. Hopefully it is. Now let's actually write a training loop to train this model. So to do that, I need to define a couple of things. First, I need to define something called the number of epochs that I'm going to train my model. So let's say set it to 10. So an epoch is essentially one pass through the training data. So the number of epochs defines how many times we are going to go through our entire training data set. In this case, it's just 4 prefixes. This is again, a super simple toy example. The next thing we want to do is define our learning rate. Remember, when we're doing gradient descent, we need to define the step size. How big of a step do we want to take in the direction of the negative gradient? We can maybe we'll set it to 0.1. Again, this is a hyperparameter, so we can modify this if training isn't converging, etc. We saw some of the failure cases associated with big learning rates. You might see the loss zigzagging around or going up in some cases if your learning rate is too big. So it's important to mess with it until you see a nice smooth curve in your loss function that's decreasing. So PyTorch defines this cross entropy loss. You can see it here. And this applies the log softmax function and then applies a negative log likelihood computation, which accomplishes exactly what we went through on the iPad. It computes the negative log probability of the target word and averages it across all of the examples in the batch. So average cross entropy loss over each prefix in batch. Okay, and the last thing we need to do is select an optimizer. So we went over simple gradient descent. To get that, we can do torch.optim.sgd stochastic gradient descent. All optimizers require you to pass in the network's parameters, which you can do by just doing network.parameters. Not too difficult. And then we have to pass in our learning rate, which we specified up here. Okay, so right, maybe I will. We will use vanilla gradient descent. You can experiment with others like Atom and stuff simply by just changing the. So you have Atom, Ada Max, others. These are all different, more complex and sometimes better variants of SGD that help for particularly complicated networks. Okay, so next we're going to write our training loop. So this loop will pass, it'll be over the number of epochs. Oops, for I in range num epochs. We're gonna loop over the training set. We're going to compute these logits, right? I'm returning those in the forward function. So I will call my network on the, what did I call this thing? Prefixes? Yeah, the prefixes, the input tensor that I made. Then I'm going to compute my loss function, the cross entropy loss. Very easy to do this. I will pass in the logits, and I will also pass in the labels, which contain the words that I'm supposed to predict. Okay, so I have computed the labels, and now let's update our params to make the loss smaller. So before we do this, maybe we can just print the loss. First, I want to see if this is working and I didn't make any dumb errors. And secondly, we should observe the loss is not changing. So why isn't the loss changing? Because we haven't actually updated the parameters using our optimizer. So when we do this, hopefully our loss will start going down. So the first thing we have to do, remember, is step 1, compute gradient. Gradient, partial derivatives of loss with respect to parameters. And I remember before I told you this was just one line, and it's literally this simple. I just type loss.backward and done. I have the gradient. I have the partial derivatives with respect to every parameter. And next, update params using gradient descent. To do this, I take my optimizer that I've created from before and just type step. I think I also want to zero the gradients. So this will, step 3, zero out the gradients for the next epoch. All right, let's put some spaces, make this more readable. So if I don't do this, the optimizer is going to accumulate the gradients across every epoch, which we don't want. So after we make one step, we want to go back, use our new model parameters to compute a new loss function, recompute the gradient, take another step. So this zero grad, make sure we don't accumulate gradients across different epochs. All right, so let's go ahead and also print out our loss function. So I'll print out the epoch that we're on and the loss. Okay, and I'll make the loss a little readable. Loss. All right, so whoops. What did I do here? Not all arguments converted during string. Okay, whatever. Maybe I will just. Oh, I forgot a percentage sign. Okay. Great. So we see the loss is going down. It started at 2.64 and now it's at 1.27. Let's see if we can make it get to 0. Let's train it for maybe 20 epochs. All right, so it's getting down pretty close to 0. We started at 2.24. This is the average loss across all the elements in the prefix. And we got down by epoch 20 to 0.17. So huge reduction in the loss. So to conclude, let's say, our loss has dropped to close to 0. But are we confident that this is actually working? So we would be confident if I can put in, say, Bob likes into this model and observe that it predicts sheep with a very high probability, right? Or if I put in Alice is and it predicts fast. So is this actually happening, or is our loss low, but our model still isn't predicting reasonable conditional probabilities? Let's see. But is it actually working? Let's see. Okay, so note that up till this point, I've been working entirely with the indices corresponding to the words, but now I might want to actually see like the probability that the model assigns to a particular word following the prefix. So to make this easy, I can define this reverse vocabulary mapping. Let's first define a reverse vocabulary mapping from index to word type. We can call it rev vocab, and I can do this by simply iterating over all of the items in my vocab dictionary. Okay, did this work? Great. I think oh, whoops, I forgot a items, so that should work. And let's just see what this looks like to be clear. So it's just the reverse of the vocab. 0 is mapped to Bob, 1 is mapped to likes, and so on. Okay, so let's just see what happens when I put in Bob likes. I know that's the first element of my prefix tensor, so I'll just call this variable Bob likes equals prefixes 0. So prediction equals network Bob likes, and since my model is set up to take in 2-dimensional inputs, right, where the first dimension is the batch size, I need to feed it, if I'm interested only in this Bob likes prediction, I need to feed it a 2D matrix, not just a single vector. And so I need to make this batch size dimension 1. So right now, whoops, where am I? Down here, this Bob likes variable, if I print its size, is just a 2-dimensional vector, right? Because it has the indexes for Bob and likes. And what I'm going to do is unsqueeze, which means I create a new dimension and I put it in the first dimension. And this is going to be the equivalent of my batch size, and unsqueeze just makes the new dimension size 1. So if I do this, now you see it's a 1 by 2, and now I can pass it into my model. So if I do this, now I get a prediction. Let's see what the prediction looks like. Again, these are the unnormalized logits. So maybe to make this more readable, let's go ahead and apply the Softmax function. Oh, I already imported this, right? Softmax prediction dim equals 1. Let's just call this probabilities. Call it probs. We'll call this logits. We'll call this logits, and I have to specify the dimension of 1. So if we print probs, now we get the actual probability distribution. These are not the log probabilities. Just to be clear, these are the raw probabilities. And if you'll notice, this is also a 1 by 11. So if I want to get it into, if I want to flatten it, so basically do the reverse of this unsqueeze operation, I can do squeeze, which gives me just a single vector. And now I can find the index that has the max probability, right? This is what the model is actually predicting. So I can write out the argmax index equals, just use the argmax function. And if I want to get, so this is going to return a tensor object. If I want to actually use this to index into my rev vocab mapping, I have to use the dot item, which will get it back into just a Python number. So let's go ahead and make this more specific. So given Bob likes, the model predicts the word as the next word with, let's give it, let's say, for F precision, probability, and we will put in the rev vocab of the argmax index. So this is going to reverse map the argmax index into a word in our vocabulary. And let's also look at the probability of that word. Okay, hopefully this worked. It did not. Okay. God, I'm really struggling with the, oh. What have I done wrong here? Oh, I forgot the parentheses. Okay, so given Bob likes, the model predicts sheep as the next word with 0.7851 probability. I'm gonna get rid of this to make it easier. And this is not great, right? There's 4 prefixes in here, so I would hope that this can get closer to 1. And maybe if I train for more epochs, I will. So let's go ahead and train this for 100 epochs. Okay, my loss is now at 0.02, so it's very low. I expect this to be a much higher probability. All right, 98.93 probability. So you see that as the loss gets lower and lower, the probability of predicting the right continuation increases. All right, so just to summarize, oh, this video has gone much longer than I anticipated, as usual, I guess. In this notebook, we've gone from raw just text of 4 different sentences to a fixed window neural language model that can predict the next word given any of these 4 prefixes. So of course, this is not a usable model, right? It's a very simple vocabulary. We are evaluating the model on our training data, which I said was one of the things you definitely should not ever do. But this is just a demonstration. There's no expectation that this model is going to generalize to anything outside of its training set. And so, in practice, you would want to have a separate test set that you're evaluating your model on that it hasn't seen before. Okay, so with this, we've kind of synthesized all of the concepts that we've talked about till this point, right? This notion of tokens and types, the idea of going from words to indices, which then allow us to index into an embedding matrix, right? Which is then composed using a neural network architecture, in this case, a very simple one, to get an output probability distribution, right? And how do we actually train the model to produce a better estimate of these conditional probabilities? We first define a loss function that tells us how bad the model is doing. We compute the loss on our training data. We compute the partial derivatives. I didn't actually get to show you much regarding this step because it's again one line. So we do backpropagation all in this one line, and we do gradient descent in this line. And once we loop over our training data a bunch of times, we get a model that achieves a very low loss, and we see that the model is doing a pretty good job at predicting what it sees in its training data. Bob likes sheep. Okay, so for next time, we're going to focus on the actual architecture that goes into the forward function here. So we talked about 2 different ones. In addition to this fixed window model, we talked about the recurrent neural language model. But for next time, we're going to move to the state-of-the-art composition function, which is the transformer. So we're going to start with self-attention, which is a basic building block of the transformer, and then move on to how the forward propagation actually looks in the transformer. This is all setting up for next week, where we talk finally about the applications of large-scale transformer language models for solving NLP tasks that are not language modeling. You all are probably sick of just looking at language modeling by this point, but I promise soon we will advance past this. But it's very important to get familiar with how these models work and how they're trained and so on. All right, great.